Been a while. Hope you enjoyed your break. Little break. All right. The last thing I rushed in the last lecture was something called, I call it a Marriott's Flask. It was we had a flask full of water with 3 holes in it. And most of you accurately predicted that the bottom hole would shoot things out faster. Do you remember why? Pressure, good. What about it? Yeah, there's more pressure at the bottom, down here. Pressure was density of the fluid, so in that case it was water. Gravity, it's feeling the weight of all that fluid above, on top of it. And how much? The height, how much above it you have. And someone asked, excuse me, I'll apologize now for coughing a lot. I got a tickle. The cold's starting. It's in the annoying stage where coughing doesn't seem to help, but it makes you cough anyway, so I apologize now. Who was it? Was it you or about weight density? Somebody asked about weight density last time. Your book refers to weight density. That's this term. I don't like to use it because I don't see it's necessary, but so I wanted to explain it more. Remember, density is mass over volume, the ratio of mass to volume. So if I substitute that in for density, you get mg over v. You can think of it as the weight per volume. And the author chooses to call that weight density. Yes? Correct. Yeah, I'm 9.8 meters per second squared still, yes. Yeah, so, because the author in the text keeps calling weight density. Kind of has a shortcut to sum up this dg. I think because some people, density seems confusing. Because you can represent, since density is mass over volume, you can represent the mass as density times volume. And that seems weird to people sometimes. Same here, we got density thrown in now instead of m like we were used to. So he's calling it a weight density. But it's just the ratio of weight to volume. Weight density. Density should make you think, oh, volume's involved, how it packs into a certain space.
You don't actually put it 9.8 for G. How can D equal M over V times by 9.8?
D here, if I substitute in for what density is, it's mass over volume. So that's what I did there. You still have the G here, this G there. This is weight that we've dealt before, and that's still volume. So this term over here, he refers to as weight density. And I just wanted to explain that better, lest that was confusing anybody from the text to me. It's explained well on page 230 at the bottom, again. Or you can rewatch this later. So, down here, as you said, since it has more water or fluid on top of it, yes, the pressure is larger down here at the bottom than anywhere above it due to the weight of water. And I also wanted to show you that if you take a parcel of water, say that bit, arbitrary size, it has a certain mass. Up here, it has gravitational potential energy, doesn't it? Remember that? Well, when it's down here coming out, it has what form? kinetic. And since total energy is conserved, however much it had up here, by the time it shoots out, it should be now in the form of kinetic, but the same total. So that gravitational potential energy equals the kinetic. That at the top equals this at the bottom. You with me? Just for fun, let's show you. That's what they equal. And if you solve that for V, you can figure out how fast the water shoots out of that hole, given how much water is above it, that H. Because it's just the weight of that water, and to show that it corresponds. We're not like making up new stuff here with fluids. It's still, total energy has to be conserved. And interestingly, if you just took a ball from that height and dropped it, by the time it got down here, it would have accelerated to a certain speed, right? What speed would that be? Same speed. I find that fascinating. That water, when it goes that far down, shoots out with a certain speed. It'd be the same speed as if you just dropped a ball from the same height, if that ball had the same mass as the water. Just because energy has to be conserved. It doesn't matter what's going on as it comes down. And that increased pressure is what shoots it out. But now that it's out, it's all in kinetic energy. You know how fast, you could know how fast it's going. Okay, I want to do this demo. Question, yes?
So this has velocity, right?
This has velocity. The water has velocity? Yes.
Are you talking velocity or volume?
This V is velocity. Kinetic energy is the energy associated with motion.
So if I want the rate of change, it would be time for rate of change.
If you want the rate of change of what?
In the calculations, you can do that. You can measure the rate of change of, like, the height of the water, how fast it's going down. So you'd have to have a time.
Definitely, for any rate you would need time, yes. If you wanted to figure out how fast it was falling, the rate that it drops, that would be as h changes over time. That would give you the rate of it decreasing, or the rate as it shoots out. Yes, but for that you would need time. Again, here, gravity is doing work on the water. Work is our way to change or transform energy. So it goes from potential to kinetic. How long that takes is work over time, a change of energy over time, and we call that? Thank you. A change of energy over time, work per time. How fast you make that change, the rate, power. So how fast this happens would be power. I get to climb on the table again. Power is a rate of change, the rate at which you use energy or it transforms. These bricks are 26 pounds. They're lead. And I got a tube connected to my water bottle, hot water bottle. If I raise this up, what do you think will happen? It's open here. There's a hole to the air. It's connected in to fill this up. But we got, like 50, 2-ish pounds on here. You think the pressure will raise it? So if I stand up here, we have this pressure head. This column of water has a certain weight. So yeah, the pressure down there is increased. down here. And that pressure is allowing these to rise. Not much, but can you see them go up? So again, I think a dramatic way, semi-dramatic, to show that yes, a column of water, it can exert a lot of pressure, enough to lift 52 pounds. But something else is going on here too. I'm not holding water up anymore. Where did it settle to? About here? Now this is telling me that the pressure needed to lift these up, to hold them up, is balanced by this column of water. In other words, somehow the weight of this water is lifting and holding the weight of those bricks. Do you think the forces are the same? Do you think the weight of this water weighs the same as the bricks? So what else is happening? There is air pressure going on. Good. The air pressure on this is the same as the air over here. So in that case, they're equal. I haven't got to that chapter yet, but good to think ahead. So we have the same atmospheric pressure.
Because the surface area in the tube is smaller than the surface area by the bricks, it multiplies the force.
Yeah, we're multiplying the force. A simple machine, in a sense. A hydraulic press is what I've just done. This area is really small. So this little force is this column of water here, a little over a meter high. That water can't weigh too much, relatively speaking, but it's acting over a really small area. Where this is a lot of force, but it's spread over a bigger area. So I worked out some numbers so we wouldn't have to figure it all out, and I'll put those on the board. You can see that if I lower it, it now does not have enough water over here creating enough pressure to maintain this. So the bricks go back down, and as they do, they shove water back into the water bottle. If I make it lower and kept it here, this would exert more, and it would start coming out of the hole here that I'd have to clean up. So I'll stop about there. Okay. So you can see how this works. I figured out all the numbers so we wouldn't have to. So we have my crude drawing, a bottle with a tube, woo, into the hot water bottle, board, big bricks. Okay. So on this side, the weight of the water, the force down, came out to be less than a Newton. So if you took that water in the column and weighed it, less than a Newton. The area of this tube is pi r squared equal the really small number. 0.0000636 square meters. What?
Is that the force of the water?
Yes, it's the force of the water. The area over which that force acts is a really small number. And I did it in square meters so we could stay in standard units. Over here, this force came out to be 233 newtons, and the area, once it's curved, that the board actually exerts on the hot water bottle was significantly more than this. The ratio of those areas, I figured out for you. It was 325 times the area on the hot water bottle. So how do you expect the forces to vary? 325 times, which you can figure out, and it does. What's staying the same here is the pressure. Once it came to equilibrium there, the water settled at a certain height. And the pressure down here was caused by this column of water. The pressure over here was caused by the weight of the bricks on that area. This force over this area and this force over this area. Same pressure in the tube and the bottle. So on this side we had a big force over a big area. And over this side we had a little force with a little area. But the pressure stayed the same. And that's how a hydraulic lift or press works. And this principle is called Pascal's principle. It works because the scientist Pascal realized that the pressure in an enclosed container, like this tube and hot water bottle, equally transmits the pressure throughout. So the pressure at this point is the same over here. It's a fluid. It can push everywhere in all directions. And that's why this was the same. And allows us to multiply the force. So for a little weight, we can lift a big weight. This is how they can lift your car. They just spread it over a bigger area. Yeah.
So if you had a height to that, then you can figure out how much pressure is being exerted upwards on the bricks.
Yes, if you want to know this, yes. Yeah. This height, you can figure it out, from here to here. That's the H. And pressure is density times gravity times H. You plug in the density of water, gravity, and that height, you'll get the same pressure as you get by figuring this out or this out. And if you want to try that out, that was, when I measured it yesterday, it was 115 centimeters, 1.15 meters. You saw that here. It was a little bigger than a meter. See, I was standing up there. So the water level was about there-ish. So everything's consistent. The pressure created by that water at that height is what allowed us to lift that force over that area. If we made this area bigger, we could lift even more weight. Yeah?
So hydraulic systems, as I understand it, they vary in size depending on the force that you need to
Yeah.
support the system.
Yes, hydraulics do vary in size. Simplified version.
So like cars, brakes, like the brakes, that's hydraulic. It seems small, but it still provides enough force to stop a car. So I'm kind of confused. It's not like a big cylinder inside. Because they're a little bit different.
Your brake system does work on hydraulics, and it is multiplying force. You're just not able to see the two areas. But the essence there is you're pushing on a brake, and you don't have to push very hard. So you have a little force. But it's acting over a smaller area. That provides a pressure in the fluid. Pascal's principle says that pressure is equally transmitted over to here, everywhere. So if you have that same pressure acting on a bigger area, you can get a big force squeezing your brake pads onto your wheels and allowing you to stop. So you can apply a little force on the brake pedal and get a big force out. Simple machines can multiply force. What do they not multiply? Energy. Good. In this example, who's going to have to move further? This piston or this piston? If we're going to have, they're each going to do the same amount of work because it's not magically multiplied. Then the one with the big force versus the one with the little force, the little force has to move a lot further than this one. So you have to move the brake pedal significantly further than the actual brake pad moves. And likewise with this. I had to lift the water up, a bigger distance, where this only raised up a few inches. Because energy is conserved. We're multiplying force. And that all works because of Pascal's principle. Here's maybe a more fun way to do it. Anybody ever made a hovercraft before? I've done them with little CDs or balloons, but here's one where the air is going to come out of these holes. But I'm going to put it in this one. This is going to provide my pressure. Since I can't talk over it, it's not much pressure. I can stop it. It's not much pressure, but it'll equally be transmitted underneath this area. So, little area, but I'm going to spread that pressure over a big area. You do that, you can support a big force. Would anybody like to take a little ride? It would hold you, Brian.
Surfing?
I'm going to have you sit so you don't fall. If somebody wants to come try it. Oh, we got a volunteer. The thing with this is is mainly a balance issue, so we eliminate some friction. So we'll have you sit in the middle, facing here, so you can control it. And we'll see if it really does lift you up, and we can scoot you along the floor a little bit. Yeah, it just moves left and right, so when you're ready, scoots that way a little. There you go. All right, turn her off. Thanks. I appreciate it.
How bumper cars work?
Bumper cars. I don't know if they ride on a cushion of air. I've never checked that out. But it would make sense. But again, you want to be able to lift something, you don't really have to provide much pressure if you can spread it over a big area. Rewrite the formula. If pressure is force over area, then force is pressure times area. And so for a given pressure over a big area, you can get a lot of force. And I've always wanted to do this. You'll be the first. It sounds kind of simple, I hope, that the pressure, is equally transmitted throughout an enclosed fluid. That's Pascal's principle. But I want to visualize it in your mind. So, we got something called a Pascal Syringe. I'm going to fill it up. I put some fluorescein dye in this water. It's fluorescent. It's the stuff the eye doctors put in your eyes when they want to look at your eyeball. Let's see if I overflow that. This little syringe, it has little holes down here. So I'm going to fill it up. Here's my plunger I'm going to stick in the top. Good enough. Oh, what's going on? Well, one light bulb should be enough. Okay, sorry, I learned. Camera guy, focus on me because I'm turning the lights off. Let's see, how many lights? Maybe this many. Makes a good mess, too. Oh, yeah, this is going to work. All right, so the idea is I'm going to depress the plunger and exert pressure at the top. It's equally transmitted to the bottom, and each of those holes, it's going to squirt out at the same speed. Are you ready? Whoop, not on me. Shh. Did I get you? It doesn't stain. And there we go. I'll get the lights back on for you. I think it's always fun when you can make something fluoresce anyway, so there. Now hopefully when you're studying this stuff, maybe you'll picture that again and how it comes out equally in all directions. Then we get projectile motion. Did you see him curve? But we won't go back to that. Okay. Enough about Pascal's principle. Let's do buoyant force. How many of you have gone swimming or in the bathtub? Have you ever weighed yourself while you're in water? It's fun. You have to someday, if you can do it without breaking your scale. Do you feel lighter? That's called buoyancy. And there's actually a buoyant force acting on you. So we know how to deal with forces. And basically, you weigh so much in air. You know your weight. You step on the scale, and that's going to read your weight. But when you're in water, or any fluid, that fluid is going to exert a net upward force on you. This is a net upward force. If you have the book draws this well, an object submerged underwater, at this height, you have a certain pressure. At this height, you have even more pressure. I'm sorry, what?
It's the same idea as the vest that scuba divers use. The more air that's inside it allows you to go.
Yes, scuba divers. Yes, as scuba divers go down deeper, there's more pressure, and so to come up and down, they have to regulate air in and out of their system. Yes, to understand why there's a buoyant force on you in the first place, whether you're going up or down. If you're underwater, if you're in a fluid right now, the air. There's a buoyant force acting on you due to the air you're displacing. But we'll get there. Here, the pressure here is greater than the pressure there. And since Pascal's principle says it's equally distributed around it, there's a pressure on the underside at that point that's larger than the pressure at the top. There's a small difference. That difference, that net resulting force, is what creates the buoyant force. On the sides, they'd cancel out. Can you see that? But something that has some shape at all. The bottom is under slightly greater pressure than the top, and you get this net upward force that we call buoyant force. And it can be measured by just the difference of weighing yourself in air or in water if you're submerged. Okay, we're going to do another experiment. It'll involve clicker questions, so you can go ahead and get those ready while I pull up the questions. What I'm going to do, take this scale, show you that this cylinder fits exactly into here. It's the same volume as the space. So pull them apart. The hole inside is the same volume as this. You'll need to know that. And then I'm going to hang this from the scale. It'll be accelerated downward with gravity. And you can get a reading. About 6.5 newtons is what this stuff weighs. If I submerge this object by putting it underwater, what will the scale do? I want to see what you guys think. That's the first question. So pulling's open. There's the session ID number in the bottom right, like normal. So when that object, that cylinder, when I submerge it, I won't let it touch and rest on the bottom. I'll just make sure it's underwater. What will happen to the scale? We got most of you already. 10, 9, 8, 7, 6, 5, 4, 3, 2. Did you get it? I haven't ended yet. Are you logged in? Do you want more time? Is it working? Are you good? Okay. 80% of you think it will decrease. Somebody please tell me why you think it would not decrease. Because you might be right. I'll do it in a second. Anybody that thinks it won't decrease, would you mind sharing with us? Well, I was hoping you would, but yeah.
I'm just thinking that maybe because it's such a small area that the force won't be as great to make it decrease.
Because I'm using a small cup, small volume, maybe it's not sufficient to see a decrease? Okay, see, that's logical. That makes sense. Let's try it out. So 6.5 newtons. Let me raise this cup up so it's underwater. And what's it read now? About 5 newtons. So it did decrease about 1.5 newtons. So that's what we call the buoyant force. All right. It does decrease because the water is exerting a net upward force on the cylinder. It's helping support the cylinder a little, so the scale doesn't read as much.
That's why animals that live in the ocean can be much bigger because the water weighs.
Very good. Animals in the ocean, like a whale, can survive in there and be massive. You get a whale on a beach, one reason they can't survive is because, they crush themselves because they no longer have that big buoyant force on them. Yeah, they suffocate. Okay, next one on this series. I'm going to do it again, submerge it, but when I do it this time, I'm going to, you probably noticed, or maybe you didn't, some of the water goes up in the cup. I'm going to let that overflow and catch it. That water that the cylinder displaces has a certain volume. How does that compare to the volume of the object? That's what I'm getting at here. The cylinder is so big, it's going to displace a certain amount of water. Which one will be bigger? While you guys finish, I'll set it up. So I filled it up. It's running out this hole. So basically it's like I filled it up to the brim. If I put anything in there now, it's going to make water overflow. This is empty. So now when I submerge it, it'll displace water and we can catch it. Let's see what you guys thought. Oh, 10. Still have to count for you. 9, 8, 7, 6, 5, 4, 3, 2. Okay, 1. Some people don't want to play. All right. 72% of you think it'll be the same volume. Let's find out. If I can do it without spilling. So notice again, we're at 6.5 newtons. You know what that should go to, right? Let's lift this up. It's displacing water into here. There we are. This still swings, so I'm not resting on the bottom. And we got this much. Do you remember that that cylinder was the same volume as this? So if I pour it back in, which I'll do in a moment, let's just do it. There. And it exactly fills that volume up. So any object that's underwater displaces a volume of water equal to its volume that's underwater. If only half of the cylinder were underwater, it would only displace half its volume of water. But what else do you notice about the scale? What's it back up to? 6.5. Okay, that's your clue for the next question. To really drive it home. Pulling open. Poured it back in. So that displaced water has a certain amount of weight. How does that compare to the buoyant force? Hopefully you realize you just saw the answer. But I'm making sure here. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. They're the same. 82% of you think they're the same. The 82% are correct. We displaced the water. We saw that it was the same volume as the object. When I added that water back to the system on the scale, it made it go right back up. So the water that was displaced weighed 1.5 newtons because it added back to the scale. What was the difference of the weight in air versus in water? 1.5 newtons. So yes, the buoyant force is equal to the weight of the displaced fluid. The buoyant force is equal to the weight of the displaced fluid. We started at 6.5 newtons. When we submerged it, there's now a buoyant force acting on it, and it dropped 1.5 newtons. It also displaced water that weighs 1.5 newtons. We put it back and we got it back up. Those of you that did not get that correct, do you understand? Before I answer your question, Brian, this is called Archimedes' principle. Archimedes' principle. It's in your text, but that's what it means. The buoyant force is equal to the weight of the displaced fluid. However much it displaces, if you could weigh it, that's the buoyant force. Okay. I would agree it is similar to Newton's laws. but more the third law than the second law. Let's see here. If I put this up here, and I don't remember what this was, let's just see. Well, I thought it was. Whee! Having fun now. Okay. We'll get it close. All right. Basically, I'm getting this sort of balanced. If you were watching me at all, you can see it's close. When I throw this ball in here, it floats. But this side's heavier now. Why? The ball is pushing down on the water. It's its weight. The water is supporting its weight. They're equal, aren't they? Or else it would be sinking or rising up. It's not moving vertically. Well, the water then is feeling a recoil and being pushed down on the scale with the weight of the ball. And so the scale reacts. So in that sense, we got Newton's third law is happening. Even if, let's take the ball back out, I dip my finger in it, I can push on the water, so to speak. And look, it goes down. I'm not pushing on the bottom of the beaker. I'm not even touching the beaker, but my finger's underwater. This much of it's underwater. So how much water does it displace? The same volume that's underwater. And that water that's displaced weighs something. That's the buoyant force that the water is pushing up on my finger with. It's helping support my finger. If it's pushing up on me, then I'm pushing down on it too. And that's what makes the scale dip. And we get things that sink and float. And that's how I think we're all end. And we'll get to atmospheric pressure. Let's just float a few things. If you ever want to emphasize the buoyant force to someone, try to submerge a balloon. You can clearly feel the force pushing back on you, the buoyant force. I'm displacing its entire volume of water. And that's a lot of water, so it weighs a lot. The buoyant force is big. I can feel that. Right now, it's not displacing much water, is it? Because not much is underneath. So the buoyant force is actually less than it is like this. Yes?
I just want to, first I want to make sure I understand the concept, and then I have some trivia.
Yeah.
The first is an object's buoyancy depends on the density of the liquid it's in.
The buoyancy, the buoyant force is affected by the density of the fluid it's in, yes.
Technically, if you were, in the air, if you just standing there, there is some buoyant force on you.
There is a buoyant force on all of us right now because we're displacing air, which is a fluid, but it's less dense than water.
And now let's get to the trivia. If I was on top of a mountain, where there's less air density and less air pressure, would I weigh more or less than if I were in the air?
Great question. And what do you think?
It's kind of difficult because I would imagine that you'd also weigh, there's also taking the back because you were closer to the center of the earth.
Okay, well, we'll assume, yeah, gravity doesn't change that much from the ground to, say, Mount Everest. So gravity isn't going to be the dominating factor. But let's say you stood on a scale down here and weighed 180 pounds. And you went up to the top and stood on that same scale. Do you think the scale would read less or more? Where do you have a bigger buoyant force, do you think? Lower. Because there's more atmosphere. There's more air you're displacing down here where it's thicker. Up here the air is thinner, so you don't displace quite as much. Same volume, but there's less air there, so that the amount you displace will weigh less. So the buoyant force on you up here due to the air is less. So the air isn't helping hold you up as much as down here. the scale would have to support your weight more, wouldn't it? So it actually would be a higher reading, slightly, if you had a sensitive enough scale. Because down here, the buoyancy is helping you. If you could take your scale and put it in the pool and stand on it, it'd read less, because you're being buoyed up more, like down here in the air. Up there, you're being buoyed less.
Yeah, it's kind of away from the idea of weight, but like athletes that live in mountainous regions, when they go down to lower sea level areas, are usually able to run much further because some of their lungs are huge, they pack in a lot of air. And so,
Yeah, athletes can change the volume of their lungs. But it also has to do with the amount of oxygen in the air, too, that the muscles need. So there's a couple things playing there. Let's finish these, let you go. Here's a boat. It's aluminum. Aluminum is more dense than water. But because I've spread it out over a bigger volume, this boat has a less density than water. Things that are less dense than the object they're in float, like this. What if you make it more dense? See, same mass, right? But it's in a less space. So this is more dense, correct? Will it sink now? Still float. So it still must be less dense than water. Let's make it more dense. Now what? Nope. All right. Same mass, less volume, more dense. Is it more dense than water? Yes. Now it sinks. Things that are more dense sink.
if you put that surface area further, even as if you got denser, put it further,
You mean if I spread this out really wide?
kept the density.
Well, by making it wider, I'm increasing the volume. Thus, its density would decrease. How about root beer and diet root beer? I call this root beer float. Diet, why does it float? It must be, the can must be less dense than water. And regular must be more dense. Because it sinks. Less dense floats. Why? It's the sugar content. This doesn't have sugar. They replaced it with something else. So less mass for the same volume makes it less dense. And I thought this one was fun. Found these. These are both concrete. Same volume, pretty much. But concrete can be made to float if it's less dense than water. How does this become less dense? It's more porous. There's more air in there. This is lighter. Now, I want to ask you, if I hold this one underwater, which one feels the greater buoyant force? Careful. Same. Very good. They're displacing the same volume of water, aren't they? So they have the same buoyant force. But who's lighter? This one. Its weight is less than the buoyant force. So it rises up. That's why it floats. This guy's weight is more than the buoyant force. So the weight wins and it sinks. All right, I'll leave you with that.